no course on algorithms would be complete without graph algorithms. Graphs are central to many problems in computer science. They help structure information that's complex and reflects real-world realities. And in this module today, I'm going to talk about a very specific kind of algorithm, namely the ability to search and traverse over a graph. These graph structures are useful in many domains. A graph can represent relationships between items, not just the items themselves, like we've seen in collections. For the purposes of this module, I'm going to restrict myself to what are called simple graphs. These are the most common find that you'll find in computer science. A simple graph is one where there's no more than one edge between any two nodes. And it also prevents loops, where you might have an edge that starts at a node and loops back onto itself. But even with these minor restrictions, these graphs are quite powerful in capturing many kinds of information. Here is a sample graph that we used in this lecture. There are 5 vertices, V1 to V5. Among those vertices, there are a number of edges. In this case, also 5. As you can see, every edge connects 2 distinct vertices. In this particular graph, it's known as an undirected graph, in that the edges have no particular orientation. If I have an edge connecting vertex V1 and V2, for example, I could just as easily have said there's an edge connecting V2 and V1. With this relationship being maintained by a graph, there's a number of questions that I might want to ask. And we're going to talk about one today. If you've ever solved a rectangular maze as a child, you may have your own techniques for solving that. But as mazes get larger and larger, at some point you have to come up with an algorithm for searching through the maze, because it's not something you can just look at and solve. If I think about a maze as having an entry point and an exit point, I need to somehow capture the information stored in the maze. And I don't just want to say there's a wall here or there's a wall there. I want to capture the relationships between the different squares or cells of the maze to know whether I can move from one cell to the other. If I have the maze captured, then I should be able to come up with a way of traversing that maze from that start to the end. And for right now, I'm not concerned about how long it takes to do the maze. I just want to find an algorithm that will solve the maze for me. Now, given this particular maze here, you can quickly sight your way through it, starting at the top, making some small little turns, and eventually ending up at the end. In this solution, I seem to have avoided any dead end, but that's just because the maze was so small I knew how to avoid them. In this maze, how do I capture the relationships between all these walls? One way to do so would be to consider this maze to be a graph containing, in this case, 25 vertices, each one representing a different cell in the maze. And I can move from one cell to the other when there is no wall between the two. And so in my graph, I have an edge between 2 vertices when they're neighbors and there's no wall between them. And so that maze solution you see at the top can be codified in the graph below by imagining that I'm starting at that node marked in yellow at the top, and then traversing the graph, which means advancing along an edge to a neighboring vertex. And finally, the goal is to end at the vertex in the middle of the bottom row. So if I can find a way to represent the graph, the maze as a graph, then my traversal algorithms will be forthcoming. There are many choices that I have. I know to start with, I'm going to start with a set of vertices. And I use the word set because I want each vertex to be distinct and unique. I'll also have a set of corresponding edges. Once again, knowing that no more than one edge exists between 2 distinct vertices. But I have some choices in how I go about storing the graph. And in computer science terms, these have been called the adjacency matrix representation or the adjacency list representation. They each have their strengths and weaknesses. The adjacency matrix is suitable when you have a very dense graph, which means you have lots of edges. And so you want to store them as compactly as possible. The adjacency list is when you have a sparse graph, where there aren't that many edges. And so you can take other techniques for storing those edges to make it more efficient to process them as you're doing your operations. this is a rather busy slide that tries to sum up my two choices. Imagine that I have a sample graph that represents the different cities in New England, and I want to try to travel between them, and so I've got mileage between them to suggest how long it might take, or that could be actual mileage. When I look at this graph, it's storing a lot of information, but of course there's some information that's missing. I don't, for example, have any edge between New York and Hyannis. I only have edges from New York to Providence, and then Providence to Hyannis. So if I look at this graph and I choose to represent it using an adjacency matrix, that's what you see in the upper right-hand corner of the slide, I have a full two-dimensional matrix where every row and every column represents a city. The diagonal going down the matrix all have the value 0 because that represents the fact that there are no edges from a city to itself. However, the other values could have a number that's positive, which would reflect that there is a known edge between, for example, Boston, in this case, to Providence. There's a direct edge between those two. When I have a 0 in one of those cells, that reflects that I have no edge between those two. So if I have this representation, it's a rather compact way of storing a large number of edges. But if I don't have a large number of edges, then this graph would be rather sparsely related in the matrix. And then on balance, more of the cells would be zeros. And so you would turn to another representation form known as the adjacency list representation. Here, I'm going to keep a list of all my vertices. And then for each vertex, I'm going to keep a list of its neighbors. And so I'm using this dynamic structure, which is flexible. Sometimes a vertex might have only one neighbor, as you see here with Hyannis and Providence. Sometimes it might have 3. The same information is being stored in both representations, so there's nothing lost. However, I have more efficient algorithms depending on if I have an adjacency matrix representation or if I have an adjacency list representation. And so my legend in the lower left-hand corner quickly summarizes the differences between these two approaches. If you choose an adjacency matrix representation, you're going to set yourself up for what's called order v-squared storage. Recall how we have two metrics for comparing algorithms. I've got T of n, which gives me my performance. I've got S of n, which gives me my space requirements. In this case, my space requirements are on the order of n squared. So for very large graphs, that could quite possibly be an inordinate number of edges to store. The alternative is the adjacency list. In this case, I'm storing all my vertices, but I'm also storing just the edges that exist. And so the order of the storage is now v plus e. In fact, you might notice that each edge is stored twice, but as we've known with algorithmic analysis, the constants don't matter. So it's still order v plus e space in how I store that information. They have other attributes as well. If you want to determine whether a particular edge exists, the matrix representation is ideal. It quickly tells you, and in constant time, is there an edge between two cities? In the adjacency list representation, you have to search through your list. Now, as long as the list is small, you can consider that to be a lightweight operation. But you can see the division point here. If you have a dense graph which has a large number of edges, you should tend to find a representation that's based on a matrix. If you have a very sparse graph where there aren't that many edges, then I would go with the adjacency list. Ultimately, however, it doesn't matter which one you choose. You're going to be writing some algorithms that process them. So let's consider traversal. You've seen it with binary trees. I guess you've seen it with binary arrays as well. In a graph, a traversal means you want to start at some vertex and wander around through the graph, only traversing edges that exist, and end up at another vertex in the graph. The real trouble is, how do you record a vertex you've already seen? How do you start at one and remember this information? And the basic idea, as you see here, I've taken a different route through that same maze. In this case, I've done a dead end. And if you were doing this with a pencil on a maze, you would no doubt leave a mark in the maze itself, and then you'd go on your way. So I need to find some way to leave a mark that I've visited a certain square. We're going to use colors, the concept of colors, to be associated with each vertex. And that's what I'm going to use to keep track of my state as I'm traversing a maze. There'll be 3 colors that come to mind. We'll start with white. If a vertex is labeled or colored white, it means that I haven't yet visited it. That's the default case. As you start to traverse, you start to inspect some squares that exist. And we use gray to note that this particular square has been visited, but I haven't yet visited all of its neighbors. This reflects the idea that you're traversing the graph and you haven't yet decided if that's the final way to get to the end or if there's a dead end that you have yet to encounter. When you actually have hit a dead end, and that means that that particular vertex is not part of your search from your source to the end, then I'm going to mark that graph, that particular vertex, as black. And that is how I'm going to record the status for each vertex in the graph when I'm undergoing a traversal. I'll start at some particular point and I'll work my way to some ending point that's desired. So if I take this small little example here and demonstrate on that same graph the coloring scheme, you see that it starts off the same way, but then it makes this inadvertent move to the upper right hand corner where it suddenly hits a dead end. Now all those vertices are marked as black to state they're not going to be on any solution to the terminal. And then you work your way back to a branching point that has another direction that you can go on, and you continue in that way. And so what the graph traversal suggests is that you start at some particular point, and as you wander your way through the graph, you color the vertices gray when they're leading you to your solution. And then eventually when you get to the end, you stop. And so if I look back on the colors, that in a way gives you the path that you've chosen to get to the end. I will also find another way of recording the traversal solution so that we can easily recover it once we're done. So the particular algorithm that we're going to use to traverse a graph is called the depth-first search. There are others which we'll get to at the end of this module, but a depth-first search is the one that we start with. It's a very human algorithm that says at any time I'm going to make a decision, I'll just choose a direction and keep on going. And I hope that I'll get to the end. If it ever turns out that I've made a mistake, I'll mark it and I'll backtrack or undo to get back to an earlier state and try to go on from there. It's a common approach to doing rectangular mazes. It's also common for solitaire games like cards. The way that it works is based on a recursive structure. Now, it's not going to give you logarithmic behavior because after all, when you're walking through the maze, you're only going one square at a time. So in a way, I'm breaking up the problem from a size 25, because I started with a 5x5 maze, and now I've made one step forward, so now I've got potentially 24 other squares to visit. However, that recursive progress is being marked by these colors, so at least you can be assured that you're not going to visit the same square twice. And that's going to give you the ability to demonstrate that you start at a particular location, and through the power of recursion, ensure you visit all the squares that exist in the graph, or in this case the maze. And then, if there is no way out, eventually all the squares will be marked as black, and that tells you you've finished your search. If, however, you get to the end, and you've left some that are marked as gray, you know that there was in fact a solution that got you to the point that you're looking for. So the way that this works is I'm going to record my solution as I progress. The algorithm starts by setting up two particular arrays. The first one is called the color array, and as I mentioned, it's going to record for each vertex. Is the color white, black, or gray? Initially, they're all white. To remember the solution that I followed to get from the original source to the solution at the end, I'm going to keep track of another piece of information. Traditionally, this is called pred, for predecessor. This records for every vertex that I encounter. What was the vertex that I came from? And so in this way, when I get to the end, if I want to find out the actual solution to the maze, I've got to start at my end and follow those predecessor links all the way back to the beginning. But once I have that in place, there's a method here called DFS visit, which stands for depth first search visit. It starts with a particular node, because after all, you have to start searching somewhere. From that point, known as the source, I'm going to traverse the maze. And in this case, the maze is the graph, so I would say that better. From that point, I'm going to traverse the graph, starting at that node, and then only following along to other vertices that are connected to that node by edges. As I recursively search through the maze, through the graph, I may find myself hitting a dead end, in which case I will undo. And to look at how that works, we take a quick peek at the coloring scheme here. Whenever I visit a node, I have to mark it as gray, because that's the color I use when I've got a node that I'm visiting, but I haven't yet determined if it's on my way to the solution. Then I find all the neighbors of that node. If any of them are white, it means that it haven't yet been visited. So I plunge ahead and go in that direction recursively. And that's what this recursive step shows you here. If a particular node, that first node in the graph, has two different neighbors, it will choose one randomly, and if that entire path leads nowhere, I will eventually get back to my starting point, and I will say, well, okay, that didn't go anywhere. Is there another one that I can go on? And the answer is yes, I'll go in that other direction. So this notion about undoing a move is based on this concept called backtracking, which is when you make a function call that's recursive. If that function call returns, you know that you have more to do. And that's what you see here. If the color of a neighboring node is white, I mark my predecessor link to say, don't forget, I'm coming from vertex U. And then I visit that node recursively. When that DFS function completes, it means that that entire part of the graph has been explored. And if I go back to my original location, are there any other neighbors that are white? It means that I have to continue the search in another direction. So I've got a very convenient mechanism for being able to keep track of the status of the search and the progress in this graph. When this DFS function completes, it means that for this particular node U, I've exhausted all of the neighbors that are white, which means that they're now either marked gray or black. Then I can now mark myself. I'm done, I'm black, and then I return from this recursive call. So the power of the depth-first search is in its simplicity and its ability to use recursion to traverse the graph to find unvisited nodes and traverse its way through. What I'm now going to do is show you an implementation of graphs in Python and then implement depth-first search. We're now going to implement in Python the adjacency list representation of a graph. We're going to do it in an object-oriented form and then demonstrate depth-first search over it. We're going to use the basic capabilities of Python to create a class called graph. Initially, when it's created, it will be empty. But we have to set up the structure for what we're going to have. And the way that we're going to do this, as I mentioned, is to do an adjacency list representation. So for every vertex, we want to keep track of all the edges for that vertex. We'll set up a dictionary for this purpose. The keys in the dictionary will be the vertices themselves, and the contents will be the edges that will be populated. I have to start by coming up with some methods for constructing a graph. We'll start with the first case. I want to add a vertex to the graph. And I make at least some simple precautions. I want to make sure that my vertex is a set. All the vertices are unique. So I make sure that I can't add inadvertently the same vertex twice. If it turns out that V, that vertex, is not in my list of vertices, then I go ahead and add it. And now my dictionary here starts by associating the empty list with that vertex. Naturally, I want to add edges. So how do I do that? I'm going to start with the idea that I'm going to add from this vertex from V to another vertex to V. This is still going to be an undirected graph, which means that I need to record the fact that if there's an edge from U to V, there's also an edge from V to U. So we'll do some preliminary checks here. If it turns out that the vertex is not already in my list of vertices, I'm going to go ahead and add it. This is a very common mechanism to allow a user to create a graph by adding edges only. But I also want to have the individual ability to add a single vertex by itself, which is why I have to have both of these capabilities. So if it turns out that that vertex is not in this, then I will go ahead and add it. Same thing is true of 2. If that vertex is not in my edges, which means it's not a key in my edge dictionary, and that's where I'm keeping track of all my vertices, then I will add it. And I've covered that case. Now I want to make sure that the edge is recorded from to and to from. And I want to make sure that they're only in there as a unique edge, because I don't want to have multiple edges between the same two vertices. So if it turns out that 2v is not contained in self-edges from v, what this means is I'm keeping track, in this case, of all the neighbors of that vertex from v. And if 2v is not yet a neighbor, then I want to add it. And I'll just add it to the end using append. We'll do the same thing correspondingly on the other side. If from v is not yet a neighbor of the 2, then I go ahead and add it there. Now, this particular graph is undirected because I'm not keeping track of the orientation of the edges. It's also not keeping track of any weights that are associated with the edges. We'll leave that for a discussion in another module. I'm only concerned about the structure, being able to traverse from one side of the graph to the other only by following the edges that are inherent in the vertices themselves. Once you have vertices and edges, the next natural question to ask is, does this edge exist? So this is the query. Determines whether an edge exists. Now I've set things up naturally to make sure that all my vertices already exist in my self.edges. But if someone asks for these two vertices that I've never seen before, I'm going to deny that that edge exists. So I have to make sure that those vertices are real vertices in my graph. So if this is not a vertex that I already am aware of, I'm going to return false. Similarly, if I don't know anything about the from, I'll return false. And now comes the only thing I need to say, and it doesn't matter which one you choose. I'm going to go this direction. Is 2v, is that vertex a neighbor of the edges emanating from v? And that's what I return. This is basically the graph. It's structured as a set of vertices and edges. The vertices themselves are only found as keys into the edges dictionary, but I have all the information that I need to add a vertex, add an edge, check to see if an edge exists. Let's try to put this to the test and see what we can do with it. If I have a graph, and I want to have the vertex 2 and add a vertex 3. Is there an edge between 2 and 3? No. But if I add the edge, then that edge will exist. Same time, it will exist in the opposite direction because that orientation holds. If I go ahead and add another edge, this one 2, 5, the vertex 5 doesn't exist yet in the graph, but that add edge function would do it for me. Is there an edge from 5 to 2? Yes. So this basic introduction shows me that I can create a graph, manipulate its edges and its vertices as I want, and do rudimentary queries, basically checking to see if an edge exists. Now, you find yourself starting with this premise. Now that I have this graph, I want to use it to represent a small graph. Well, do I really want to write code that consists of a sequence of add vertex, add edges? What I probably want to do is have some easier way of capturing the information and then being able to load the graph up from that. So I can go back to this earlier graph that I showed before with the 5 vertices, and I'm going to represent it in a crude way here as follows. It has a vertex 1. That vertex has neighbors 2, 3, and 5. There's a vertex 2 that has neighbors 1 and 4. Vertex 3, it has neighbors 1. You've got vertex 4, 2, and 5, and then 5, 1, 4. Now, you could argue, why didn't I just do that instead of divide this class? Well, invariably, if you use a raw data structure like a dictionary for representing your structures, at some point you want to decide, I need to add some methods or some additional state. And then it just gets more complicated if you've limited yourself at the beginning by starting with a simple structure like a dictionary. So I want to make it possible to quickly store a graph this way, but once I have that, I want to be able to load that up into my graph object. So if I have this simple graph over here, which is represented there, I want to write a function called loadGraph, which, given a sequence of edges, which is basically what you see over here, I want to go through and populate a graph instance. This is a nice little shortcut just to be able to allow you to specify a graph in a compact form without having to programmatically create it every time. So I start with an empty graph. And then for all my edges, as you know, this dictionary has keys, which are the vertices themselves, and these are the neighbors that are associated with that vertex. So for every one of those vertices, I'm going to pull it out. And then I'm going to add that vertex to my graph. Then I need to do something with these with the edges. So for every neighbor, I'm going to add the edge v neighbor. And when I'm done, I return the graph. So I've been able to do the best of both worlds. I've been able to make it possible that you could represent a graph in a very simple way, and then when you want to, convert that into an actual graph object that then can be used to ask questions. Is there an edge 1 to 4, 1 to 5, for example? And in my mind, that's a lot better than saying 5 in simple of 1, which is a Python statement that you have to write if you store it as a dictionary. And I would much rather write a function that quickly clarifies that for my code.